Hello everybody. Today we shall start on design principles of reinforced concrete elements, structural elements that we shall start today. Last few classes we have given general idea on bridge engineering, different aspects of bridge engineering, different types of bridges, and then we have discussed on how to decide that carriageway width, how to decide that width of the footpath like that. Now, today we shall go for the design principles of reinforced concrete structures. Our basic objective of this particular course to do the design, so that you will be able to do the design after completion of this course. That is our whole idea. And what we have decided today here, this is lecture 6 of half an hour duration, and that one we are considering this particular one, say lecture 6, and then we shall consider the general principles of design of reinforced concrete elements, working stress method for shear, then summary and references. So, that is our overview that we shall consider. This is the first part. So, we shall try to complete this one in 3 half an hour module, one that working stress method, and next one we shall consider limit state method. Now, if you really see that any structure you are having, that stresses may be due to either axial force, flexure, shear and your torsion, or it is a combination. If you see the structures for beams, then you will find out for beams they are mainly it is governed by bending and shear. If you consider slab, there you will find out it is mainly governed by bending only, whereas column type of structures, there you will find out that axial force and bending. Torsion generally we do not directly, we do not go for design, rather we take the effect of torsion in bending and in shear. So, this is our objective that we can find out here. Now, considering that aspect, out of these four only we are considering the superstructure, the flexure and shear. So, our main focus in this particular class, that will be on flexure and shear, how to design for that. So, we have discussed on flexure and shear only, and this is not the course of reinforced concrete design, but we require the basic principles and design methodology to go for bridge design. So, that is why we have taken that relevant codes, that first one IRC 21 2000, and also we are taking IS 456 2000. Our basic objective to know the difference and to know that how far actually it differs from one particular code to another code. That is our another objective here. Next one we shall consider that one a limit state method as per IS 456 2000 and limit state method as per IRC 112 2011, this particular one that which we generally follow. So, here also we are having working stress method also, that IRC 21 that working that also available here, but mainly we shall focus on limit state method. So, let us consider that working stress method, that let us find out for any method we should have certain assumptions. So, what are those assumptions here? That let us find out that first, let me make it here and then we shall discuss. At any cross section, plane sections before bending remain plane after bending. This is the fundamental assumption, and possibly you have learned this one either in first year or second year of your BTech course, in either in strength of materials or mechanics of solids, and if it is combined in engineering mechanics as a part of say strength or materials, there that is the first bending equation, that assumption. Next one, all tensile stresses are taken up by reinforcement and none by concrete, except as specified. That if it is not specified, then we shall not consider the tension in concrete, because the concrete tension in concrete, that one you can say that it is compared, that is almost a 10% of the compressive one you can consider. So, that is why we can neglect that particular portion here, and compared to the amount taken by the steel, that one also will be negligible even if you consider that, and that is why we shall not consider. And further, the section we consider this one as a cracked section. We shall come to that particular one cracked section, that for concrete. So, that is why we can definitely we can assume that concrete will not take any tension. The stress strain relationship of steel and concrete under working loads is a straight line. This is also another important one, because this one and that particular one we are considering as stress strain curve, that one, this one for the strain and this is for the stress strain curve, that particular one we are following. That means, we are not going to that, we are always within the elastic limit. Now, modular ratio, that modulus of elasticity of steel and modulus of elasticity of concrete, as we can definitely we can find out for steel, we can find out that modulus of elasticity for steel very definite way, but concrete it is very difficult to come to a conclusion that what exactly the value. So, that is why it is we generally we cannot, it is very difficult to find out EC, that modulus of elasticity for concrete. In that case, what we do, we find out that one in an indirect manner, that modular ratio M, which will be 280 by 3 sigma CBC. Very interesting part, we shall consider this sigma CBC, that I shall come, but please note down the 3 sigma CBC, that please note down this one here, because we shall relate that one in the next one we shall relate. Coming to this one here, this one we have taken IRC 21 2000, these values we have taken. For direct compression IRC 21 2000, that particular one are taken. So, that means bending always it is more than the direct one, and bond average that one we have taken from this IS 456, that particular value we have taken here. Just to show you this particular one, because this is the bond also is equally important. And further, we have taken from M25 to M40, because for concrete, reinforced concrete generally we do not go to M20. So, that is why you have generally we go to M35, 40 or M30. These are the 3 we go for it. Say for example, whenever we go for residential building, you will find out that we always work within say M20, M25 or M30, but whenever we go for bridges, mainly we go for say M30, M35, M40. If we go for pre-stress, then we shall go little more M40, M45, like that also you can go. So, as I have told you earlier, that whenever we are talking a span of a bridge, we mean to say that for that particular bridge, a particular type of bridge, that is also equally important. So, we shall see that one, the 10 meter span, that is for the one you can say solid slab bridge, 20 meter span, that one you can say RCC TB bridges. So, that way we can consider here 30 onwards we can consider that one say pre-stress concrete, or 25 onwards you can say. So, 30 that particular one you can say. So, these are the things, our basic objective is that you should know for a particular span, and if you understand that one clearly, then if it, I mean to say that if we can design it for 10 meter span, so obviously we can find out little less than 10 meters, say 8 meter, 9 meter, or little more than 10 meters, say 11 meter, 12 meter. So, on the basis of that we can compare whether the results are coming all right or not. So, for bridge engineering, one way you can say that we do not have many more options, we can go for few options, and if you can solve that one and understand properly what are the reinforcement, other things, then obviously that next time whenever you will do it, it will be very easy to remember that whether you are in a proper direction or not. That is the one basic idea. So, now here what I have told you in the last one, 280 by 3 sigma CBC. So, M25, M30, M35, M40, this one it means one third of FCK. So, bending compression in working stress method, that will be your 1/3 FCK. So, this one 1/3. So, what I mean to say here that 280 by 3 sigma c Vc, that means I can say 280 by FCK. So, I can compare that EM value, I can write down this one at 280 by FCK. Why I am telling that particular one here, later on in limit state method you will find out everything we are writing in terms of FCK only. So, that is why this working stress method, whatever formulation we have, all those things, assuming that these values with certain partial safety factor, not partial, that we shall come later on in limit state method, that partial word that is equally important here. So, we are considering here safety factor, and that one if we consider this one as a 3, then obviously, and here we can say 4. So, obviously, on the basis of that we can correlate with FCK only, that means we can find out that particular one with the FCK only we can consider. Now, next one we are having for steel Fe 240 as in IRC 21, Fe 415, Fe 500, and then we are having these values tension, bending, compression, then shear, that I have taken from table 10 just for as a ready reference, that I could refer that particular one, that code, but instead of that I think it is appropriate to inform you here that values where do we stand. So, these are the values, that means here whenever we are talking this particular one here Fy and FCK, these are the two parameters, just to tell you here. One parameter we are talking say FCK, another parameter we are talking say Fy. So, with the factor we are getting here something say FCK by 3 or FCK by 4, like that. That means, these 3 and 4 if I assume that one is a constant, so which is coming from the partial from the safety factor. So, I can say I can write down sigma CBC, this one it gives me sigma CBC. So, FCK by 3, that stress due to bending under compression in concrete, FCK by 3. Similarly, I can write down sigma CC, which is equal to FCK by 4. So, this particular one FCK by 4, that way we can write down. That means, everything in the working stress method also we can write down everything in terms of FCK. That is the one we can find out, that particular one. That one finally at the end of this class we would like to show that particular one, we would like to converge to a one equation where the values may be different, but the equation, nature of equation is same. That is the one our objective to take this particular lecture today in with respect to reinforced concrete. Now, main thing here that we can say that most of the cases we go for limit state method of design, but I feel it appropriate to go with the working stress method also, because that is very very important, and it will be actually easier to understand also before going to the limit state method, because whenever we are talking this particular course. So, I am assuming that you have already taken that your reinforced concrete design course, but from that particular course to this bridge engineering there is such a certain kind of changes or say importance will be there, certain clarification other things that we shall take care, and because of that only we are taking a just orientation on reinforced concrete design that we are taking in this particular one. So, first one we are taking working stress method, and this is the one say your rectangular section that we are having area of steel. This is the neutral axis, and then we are having this particular one here, that your say strain diagram, and this is the fundamental, that first assumption that plane sections remain plane before and after bending. This is the one. If it is not straight line, then it will not happen. So, this is the one we are having. Coming to this one, because of that we are having this stress diagram in concrete, which is a triangular one, that maximum here and this portion here we are having. And as we have assumed that concrete will not take any tension. So, because of that this portion there is no tension, only then the steel portion where steel is available, there only we are having that tension. This is the one we are having. I can say like that, that remember that equation, m by I equal to sigma by y. That means, if you take this section, so the stress diagram comes like this. So, this is your say y, this y, that is here, and I second moment area sigma at this particular point sigma, that we find out. So, if for wood, for steel we consider the bottom part also, but here we are assume this portion it will be very less. So, that is why we are ignoring this portion, only at the point where the steel is available, that only we are taking. That means, if we are having that one say your stress F area of steel, so you just simply multiply that. So, coming to this one here, we are having that strain diagram and the stress diagram, and tension is steel and compression, and this one at x by 3, this particular one at x by 3, that particular one is acting, and then we are getting the Z, that is the lever arm. So, this is the Z, that is very very important, the Z, that is your lever arm. So, we can say we can use a parameter k. This is customary to write down the parameter k here. So, x equal to k d and z equal to j d. So, how this j is related? The j equal to means 1 minus k by 3. So, j equal to 1 minus k, because x by 3. So, x by 3 means this particular one here is that. So, j equal to 1. M equal to already I have told 280 by 3 sigma CBC, and C will be half triangle, this triangle half FCB into x. This is FCB and this is x. So, half FCB into x, and B which is normal, that means along the width of the beam, it is along the width of the beam. Just to give you idea, that one I can say so, this is the one we are having B, this is x, and this portion FCB. So, this way I can say, that means this one half FCB into x into B. So, that volume we are getting, and that is the one is your compressive force which is acting on concrete. For steel it is very simple, T equal to FST by A into AST. AST is the area of steel in tension, and FST is the stress in steel. So, T we can find out this one, that means this C and T, this one should be in equilibrium. This C and T should be in equilibrium, and that moment, and we call this moment as moment of resistance. That means, this moment of resistance should be equal to C times either Z or T equal to Z. It should be equal, because whatever compressive force acting, because if the C and T are different, then obviously it will not be in static position, it will move. So, that is not possible. A beam, whenever it is there, a bridge always it is there in that same position. So, obviously, we cannot say that C and T will be different. At that equilibrium position, C and T will be equal. Only thing we can say, whether we have got that C and T that how much of its capacity we have achieved, that is very important. How much capacity we have achieved, that is very important here. So, this is the one we get it here, this particular one. So, whatever I have written here, just to give you that idea, x equal to k d, z equal to j d, j equal to 1 minus k by 3, like that we can write down this particular equation, we can write down. Further, we can elaborate this equation here like this, m equal to half, where from this sigma CBC is coming? Sigma CBC is coming from the permissible stress in bending. Here this one actually you are talking is a bending compression. So, we are considering that one say half sigma CBC into KD. So, please note this one here, that half sigma CBC, KD means x, then BD, that particular one we are getting 1 minus k by 3. So, if we write down that equation m equal to half sigma CBC k 1 minus k by 3 BD square. So, you can find out this particular equation here like this, you can find out m equal to half sigma CBC k 1 minus k by 3 BD square. So, that we can write down. So, what I can do it here, let us make it this particular equation, we shall use it later on. So, let us just write down that equation here, so that I can tell you. So, we are talking this one say working stress method, whatever we have discussed, and m equal to half sigma CBC k 1 minus k by 3 BD square. This is the one we can write down. Further, I can write down KB equal to m sigma CBC by sigma ST plus m sigma CBC, where m equal to 280 by 3 sigma CBC. This particular one we can write down here. Why? We shall come back to this particular one page again later on. So, here I would like to say sigma CBC equal to FCK by 3, because as per that table which is coming 1/3 of that. So, this portion let us consider that we are keeping this particular one for the time being, and then we shall come back to this page, again later on when we shall compare with the limit state method. This is a very important one we can consider here. Further, I can write down that one, let me write down here m equal to sigma ST AST, and since we are writing down that one, so let me write down draw the cross section of the beam also, so that it will be clear in all respect. So, we can say this is your B, this is your D, so B and D, and this one AST. So, we are getting this particular one here. Let us keep this particular one here. One more equation we have, this particular equation we are having here. This is very important here. So, let me just clarify this particular equation. This is the one B and this is the one XD, just to give you idea, this particular one here. Whenever you are talking that particular one here, we would like to find out that area. So, B into x by 2 kd by 2, this is the 1 Cg of that compressive force, that area. P is the percentage of steel of BD into m, because we have to convert it to the one equivalent area, because this one if we concrete. So, we have to convert that one the same area. So, m into d 1 minus k, that we can find out here. So, that we can find out here. So, b k d by 2 p by 100 b d m d 1 minus k, that we can find out. That is the one we can consider here, that this is the one for the steel and this is for concrete. So, this portion, from there we can find out many more things, we can do it here. That means, if we know the percentage of steel, then from there we can find out the value of k, or if we know the k, that what is the corresponding value of p, that also we can find out. That is why this equation also equally important. And so, let us write down this equation here also. So, b x x by 2 equal to p by 100 b d percentage of steel m d 1 minus k, or b k d by 2 equal to p 100 b d m d 1 minus k. So, we are keeping this equation for future uses when we shall consider that in our limit state method. Now, coming to this one, say balance sections, just to give you idea, when the steel and concrete both reached their capacity, then we consider that obviously that is the most optimum solution. So, but which is difficult to get, that is called the balance section. Under reinforced means steel reaches first, that is the one called under reinforced, and then we are having over reinforced, that means when concrete will reach first, which is not at all desirable, because failure in concrete will be abrupt, sudden, but whereas in steel it will give you some time. So, that is why it is always better to make it under reinforced, so that you will get warning. You will get warning in your, that if there is any problem, so that you will get certain warning. Otherwise, if concrete fails first, so it will be abrupt, it will suddenly it will happen, you will never be able to get any warning out of it. So, these are the things whatever I have told already, I have already discussed this particular one here. Now, coming to the shear, we shall come back again just to give you idea shear, that we are having shear force V, then V c means tau c B d, which will be taken by the concrete itself, and there are aggregate lock, other things. Shear force to be resisted by stirrups. So, that means remaining one V s, which we have to provide by the stirrup, and the formula that particular one for that will be V s into S V s d sin alpha plus cos alpha. That means, if you provide the stirrups in inclined manner, then you will get this particular equation. So, we can get the thing just to give you idea in one page, the same thing whatever you have given, ASV equal to Vs into S, that one ASV the total cross sectional area. If there are two legs, two vertical bars, so that means you have to take twice of that. A spacing of the stirrups, B breadth of the member, alpha angle between the inclined stirrup not less than 45 degree, sigma S permissible stress in shear reinforcement, and D the effective depth. So, this is the one, from there you can find out. How do you find out here? We can consider alpha, certain value we can consider here, and then D we know, Vs already we know. Now, the thing is that ASB and S, generally whatever we do, we find out the ASB, say 8 millimeter, 10 millimeter, 12 millimeter dia bar. Most of the cases we use two legged bar. So, 8 millimeter, 10 millimeter, like that if we use it, and on the basis of that you can find out the ASB, because you cannot give any fraction, and then you calculate the value of S, the spacing of the bar, and that then you come to the nearest certain regular number. I mean to say we generally provide something say 100, 125, 150, 200 like that, 175 millimeter spacing that we provide. The value is whatever you will get from this computation, you should provide less than that. This is the basic idea of that. And so, from the code I have given a part of it, part of table 12b, the for complete one, though you are having little more than 2. So, that particular one if you take it, again I have taken M 20, 25, 30, 35, 40. So, you can get that value of tau c. So, since you know already you know B and already you know D, so you can find out the tau c from here, the percentage of steel you have provided longitudinal one. So, tau c, so subtract from the actual shear force and provide the reinforcement there. There is certain kind of things are there, the minimum reinforcement also you have to provide, but even then also that we shall come later on whenever we shall solve the problem. So, this is the whole idea that we go for it, that is for the IRC 21 for working stress method. Similarly, we have say IS 456 where we are having that working stress method we are having, but this particular one we are considering because our main objective is that one, even if you solve it by a working stress method, what is the difference, that also you should know. You should know that one not only always limit state method, you should check that one how much it comes whenever we are doing working with the working stress method, that also you should know and you should do it. So, in summary I would like to say that working stress method for designing bending and shear are discussed here, and references means mainly I have told you the relevant portion from IRC 21, and next we shall find out that next we shall go for IS 456 2000 and then we shall go for say IRC 112 2011 that we shall go. So, with this, thank you very much.